Log on, tune in, find out. Another good idea from Cambridge.
So hello everyone. So my name's Chris Ormerod, as the slide suggests. I'm here to talk to you about orthogonal polynomial theory and connection-preserving deformations and some recent developments that have come about from joint work with Peter Forrester and Nick Witte at the University of Melbourne. So what I really want to do is introduce an orthogonal polynomial system that solves the associated linear problem for QP6. Now, this will give us a way of first solving QP6 in terms of the orthogonal polynomial theory, in terms of determinantal solutions of hypergeometric functions. This will also give us, from the orthogonal polynomial context, a way of transforming the Y's, the Pan-Lavie transcendents themselves. And this is very, very natural in the orthogonal polynomial sense. So that's the outline. The first thing I'm going to do is introduce, and many of you are experts or have seen this before, but I'm going to introduce some connection-preserving deformations. And the way I'm going to do that is just introduce you to a simple example. A simple example which will show you how to calculate the constraints, how to get the corresponding evolution in a different variable. I'm also then going to introduce orthogonal polynomials, and this is more the classical framework. What are the main key quantities of interest? And we'll use those quantities to solve the Pan-Lavie equation. Then we're going to derive Q differential equations for orthogonal polynomials. So given a class of orthogonal polynomials with an arbitrary weight, well, not quite arbitrary, but a weight that satisfies some holonomic equation. So I'm going to derive from that weight the differential equations for the orthogonal polynomials. And then lastly, we're going to look at what solutions we get from this framework and what transformations. So we're going to have explicit formula for the transformations. Okay, connection-preserving deformations. Now, it's often said that a connection matrix is the discrete analog of what the monodromy matrix in a linear differential system is. So instead of a linear differential system, what we have is a Q-different system. That is, this is a matrix linear problem where A is typically either rational, but you can transform it so that it's polynomial. So it's matrix rational in X. So you have a linear differential equation of this, linear Q differential equation of this form, and you have two canonical solutions, or well, they're symbolic solutions really. You have a solution where you divide by Q successively, and that's going to be holomorphic at 0 once you transform the problem appropriately. And the other solution is a solution that's holomorphic at infinity. Now, in terms of monodromy, you have the ratio of a solution at a point and after integrating around a pole at a point. In the same way, we've got these 2 points of interest at 0 and infinity, and we simply take the ratio. So the ratio of these two solutions, if you iterate that in X by Q, multiplying by Q, what happens is that the A comes out in the middle here, the A comes out from the left of the Y0, and they cancel, and you get Q quasi-periodicity in the variable X. So this is what we call the connection matrix. And under some conditions, you can show that this exists and that a transformation exists such that this converges. And this is just a reference for those conditions. Yes?
Do you impose a norm or an absolute value on Q?
Oh yes, sorry. The absolute value of Q is going to be more than 1 in this case. I haven't stated it, but I should. Okay. So in monodromy preserving deformations, you pick a parameter t to deform your linear problem. You deform it in some way that preserves the monodromy. What we're going to do is do the exact same thing for the connection matrix. I'm going to introduce a parameter t so that when I evolve t, and the natural evolution is t goes to qt, I'm going to keep this connection matrix. So if I have done this, then there necessarily exists a B matrix that determines the evolution in t by this linear equation. So this is the same linear equation. You've got two different evolutions. You impose a compatibility condition. That is that y of qx, qt must be consistent no matter how you calculate it. And that is this condition. So, have I missed? I should mention this, that one of the key factors is that because you form solutions in this manner, then the connection matrix may not be invertible at the roots of the determinant of A. And also q powers of those roots of the determinant of A. That means, that actually comes into, I should also show you this, which is that the roots of the determinant of A also determine, a linear problem that the determinant in Y satisfies. So once you solve that determinant in Y, you can also find out what the determinant is of B. So this gives you a set of determinantal constraints and a compatibility condition. So I'm going to give you a really, really simple example. Very, very simple. All I've done is set the determinant of A to be, it's even because it just involves powers of x squared. And I've introduced xt squared. Now, if you think back to the determinant of A, you have that a shift of t goes to qt is going to just shift where the connection matrix is not invertible. So you're preserving the poles, and that's why you choose your deformation parameter to be one of the determinants of A, roots of the determinant. Well, that's a rationale. So we've given a problem of a particular form. You have the determinantal constraints tell you what the variables of A should be. Well, actually, they give you constraints on how they should appear. So you can make these substitutions so that, and this last constraint, those all give you a constraint that constrains the matrix so that the determinant is A, as we've shown there. So one way of choosing so we have these two, A1 and C1 are going to be constrained by A0 and C0, and B0, B1 is going to satisfy this. One way of doing that is to introduce a new parameter, so we've just cut out one parameter. And I've introduced a new parameter, mu, so that it cancels out in the multiplication. So this is one way of fixing B0, B1, so that they're constrained, but the combination gives you the right determinant. You can also transform the problem out so that you divide by A0 and multiply by A0. The effect is that you can absorb A0 into the variable C0, and essentially you can set A0 to be 1. So this gives you your linear problem in A. Solving the determinant problem gives you what the determinant of B should be. Then in a similar manner, I've assumed it's of the same form. And then the determinantal constraints tell you what relations there are between the B variables. And this is just telling you how to set the determinant of B. And then you go on and you look at the compatibility conditions. So in particular, if you look at the constant coefficient, that is, if you set x equals 0, that tells you that B1 must be 1. And if you look at this condition, you have C0, C0 up. So you set C0 to be mu squared, and you have another constraint, you have another value. So the compatibility condition has determined what the values of what the matrix B should be. And then you just have this linear problem. So you have what the linear problem is in X, and you have the linear problem in T. Then the compatibility condition immediately gives you, this is the coefficient of X, gives you, say, this value of mu in terms of the new values. And that gives you this equation. The remaining condition, which is the coefficient of X squared, gives you that equation. So this is quite simple. You say mu equals y over alpha, and you get QP3. So this is just a very simple, cooked up example which shows you that, first of all, there's determinantal constraints that give you part of the information on what your linear problem should be, and the rest of the compatibility constraints, which first determine the evolution in the time variable for the linear problem, but the rest of those constraints also give you what the evolution of the associated variables in the linear problem are. So that's the main flavour of connection-preserving deformations, except it gets a bit harder. The main problem is when you have a linear problem of a certain determinant, how do you pick your extra variables? We had a very natural choice of variables here, the mu and the nu, but in higher problems, it's not so simple. Okay, so we want orthogonal polynomials that are going to solve these systems, these linear systems. So what are orthogonal polynomials? They are polynomials, so Pn is going to be of degree n in X, and there's going to exist some bilinear form in which you have the orthogonality condition. And this bilinear form is typically, say, some integral in terms of a weight function. So you have the integral of, say, the multiplication of pi and pj times some weight function over some support. That's a typical bilinear form. In our case, it's going to be a Jackson's Q integral. Okay, so from this information, you can construct sequences an and bn, which give you the three-term recurrence. So all orthogonal polynomials, in one variable at least, satisfy this three-term recurrence relation. And these ANs and BNs are our main quantities of interest, and that's what we're going to parameterize our solutions of the Pan-Levé transcendence with. So we can parameterize these polynomials. This is just for convenience. So we're setting down a notation for the coefficients of the polynomials. And this is this notation appears in, say, Alphonse Magnus's work. I'm sure it appears in other places as well. And the main reference would be for Zigo's book on orthogonal polynomials. So you can define the set of moments as the bilinear form applied to just xk and 1. And then from that, you can construct a determinantal formula for what the an and the bn are. And these determinantal formula are given there. So they're determinants in terms of the mu k. And the mu k are going to be given in terms of some integral. So we specify the Stilches, and this Stilches function is often called the moment generating function. And we define a set of orthogonal polynomials. We define a set of polynomials and associated functions. Now, if you look at that multiplication, what you're going to get is you're going to get some polynomial part, and you're going to get some, because it's a generating function and that f is a sum of x to the minus n, you're going to get the polynomial part and all the other stuff. So the associated functions is all the other stuff, basically. And you can see that if I multiply the three-term recurrence relation by f, the epsilon n and the phi n minus 1 also must satisfy a three-term recursion. Now, the reason this is epsilon n is actually of order x to the power of minus n minus 1. Now the reason for that is that the higher powers, if you will, so everything from 1 on x to 1 on x to the n, x to the n minus 2, are going to be equivalent to the orthogonality relation of x to the n with Pn. So you have these expansions which you formulate using the three-term recursion relation. This is quite a typical type of argument, and we're going to use this formula later, is that when you compare Fpn and Fpn, sorry, that should be minus 1 in the subscript, with Fpn minus 1pn, because it's a whole scalar equation, these are obviously equal, you rearrange the term, you get something polynomial on one side, and you get something non-polynomial on the other side. Well, because this is polynomial, this must be polynomial as well, and you can use these large X expansions to tell you what this is precisely. So that's what information we need from the orthogonal polynomial side. Now we've tried and find Q differential equations satisfied by orthogonal polynomials. Now our starting point is that the orthogonality relation is given by some Q-Jackson integral over some support. So here I've just defined what the Q-Jackson integral is, but many of you have seen it, but just for reference. So you have what the integral between 0 and 1, which was, I think, by Trobe. Then Jackson extended this to an integral on some support. So the first step we do is assume that the moments satisfy some recurrence relation. Now that is equivalent to the fact that the Stilch's generating function is some first degree holonomic equation. That's Q difference holonomic. So this is the equation that it's satisfied, and you can relate this back to what the weight satisfies, so which is also a homogeneous Q difference equation. And this, if you haven't seen this, the definition of dq, and in this case I've specified that it's dqx, is just this. So this is a Q difference operator. Okay, this is what determines the Q differential equation of the polynomials and associated functions in N. So if you have some y, if you have a set of orthogonal polynomials with that weight, then the solution can be written in terms of these omegas and these thetas, which are polynomials. Now the interesting thing about this is these are polynomials of bounded degree. And that means that you can construct exactly what these coefficients are in terms of sums of bn's and an's and gammas. Because if you substitute, if I go back here, you're only going to get something of bounded degree. You've got an x to the n here and x to the minus n minus 1, which is bounded degree in accordance with W. So once you have the Q differential equation satisfied by the orthogonal polynomials, it's quite easy to go back to the Q linear framework. Just take the an to be this combination. Working backwards, we have that the polynomials themselves satisfy a Q difference equation. Now we're back in the ballpark of Birkhoff theory and the linear Q difference equations. So this type of Q differential equation, this result actually appeared quite recently in Biane. I don't know if you've met him. I don't know how to pronounce his name, but that's a fair go. Okay, so you can look at the large X expansions and you automatically show that the degrees are bounded by this, which is quite simple. So given a weight, that provides you with immediate bounds for what the polynomial part of this linear problem should be. You can also just transform it so that the original problem was rational. So you can often find these f functions in terms of q exponentials and transform this to a problem that is just polynomial. I should also tell you that now immediately because the polynomials and the associated functions satisfy the three-term recurrence, the function y, which should be yn, also satisfies this equation, which is just the three-term recurrence. So immediately you have a compatibility condition between evolution in x and evolution in n. And often this will give you discrete Panlevey equations. Okay, so if you look at introducing a variable t into the weight function, then you're often, and we assume that the weight function is again going to satisfy this linear difference q difference equation in t, then we're also able to write what the differential equation in t is directly. And because, again, these epsilon n and Pn always occur in pairs, these are going to be polynomials in x of bounded degree. And we're going to be able to find them directly in terms of the an and the bn through those expansions. So we also have that you can construct this extra b, and then you have the q differential equation in t. Okay. So these are just bounds for what the polynomials in x should be of phi and psi. So we have three systems here, or well, actually the same system satisfying three differential difference equations. So you have a compatibility between the n evolution and the x evolution, the n and the t and the x. And that's represented by these equations here. You have an abundance of information. And now you also note, remember that little linear combination by comparing f pn minus 1 and pn. You look at the determinant of y, which is this, which is 1 on an times w. Now, because it's 1 on an times w, that immediately tells you what the determinant of mn is, an is, and bn, sorry.
What's W?
What's w? The weight.
Right.
So if I go back to the, so the orthogonality condition is in terms of this weight, which is up there. Or well, actually I haven't specified the weight yet. But this almost tells you what type of orthogonal polynomial you should consider in this problem. Because this weight function, w of qx over w of x, is going to determine the determinant of a.
Sorry, Chris, can you remind us how the t came into play here?
So I've just introduced a variable t. I haven't introduced how it's arrived in the
Come through the weight function.
Yeah, it's in the weight function. So w is a function of x and t.
So there's just, at this stage, an assumption that there is some t
Yes.
for which that's...
Yeah. So they're orthogonal polynomials in x, but you've introduced some t variable.
There could be many t variables.
There could be many t variables, yes. But, okay, so this, from the connection preserving deformation point, you know what the determinant of a is from this problem. So you know how to choose the variable t inside the weight. You choose it to be one of, say, the poles of the determinant problem. And that's exactly what we do. But I first should mention these are important relations. These are compatibility relations between evolving in x and n and t and n. We actually use these a bit later.
So at this stage, it's all independent of just how you introduce t in your weight function.
Yes. Yes, you introduce a weight function, but I must say that it has to satisfy a homogeneous Q difference equation which is rational. So the Q logarithmic derivative must be rational. And that's a constraint that I have implicitly used here. Okay, so this just says that you can expand and find what these thetas are, omegas are, phis and psis are directly by expanding in terms of your known values. Okay, so now we have, we know what the determinant of the problem, the associated linear problem for QP6 is. So that almost tells us what our weight should be. So a canonical choice would be the Q Jacobi polynomials. The Q Jacobi polynomials is a ratio of Q exponentials, and it's 2 exponentials. And we know what I've done is choose one of these, one of the t variables to be proportional to one pole, and one of the t variables to be proportional to one root. But again, if I have a rational determinant, a rational function, then I can always multiply and get something polynomial. And so this is now our weight function, and this is the support. So the bilinear form is in terms of this weight function, and it's an integral from a1t to a3. So using that information, we know what the mu are. You can look up Gasper and Raman, for example, to find out how to integrate this. This is a 2 phi 1 integral. And then once you have these 2 phi 1 functions, you have what these delta n's and sigma n's are. So you know what an and bn are in terms of determinantal formula. You also know what the degrees of because you can easily Q differentiate the weight function, you know what the degrees are in W, V, R, and S. So you know what that should be, oh no, that's fine. So you know what the degrees are of theta, omega, phi, and psi are. So that tells you that you're looking for a linear problem of this form. Once you transform out the rationality, so you transform out the denominator, you have a linear problem of this form, which looks sneakingly suspicious, actually. It looks exactly like the problem for QP6, except we know all the coefficients of omega theta are from the large expansions in X. In fact, I've left out one intentionally because you couldn't express this last one in terms of the other ones. But all of these variables are expressible in terms of an, bn, and this sum from k equals 0 to n minus 1. And those are 3 variables. Those are the exact 3 variables that you expect, except I need to tell you a few more things. First of all, the leading matrix. The leading matrix, because you have what omega 2 are and omega 1 are, you substitute that into the linear problem and you have what your leading matrix should be, which is your A2 in this problem. Then that's not enough information. What you also need is that the eigenvalues of your A0 must be proportional to t. So you look at the trace of A0 and you get this in terms of the bn, the omega n, and the theta. But you notice that the constant coefficient of this, which we derive from the compatibility between n and x, is equivalent to this equation, which tells you that the trace is independent of n. You also know that the determinant, which you just of A0, which is the determinant of A at x equals 0, is independent of n. So that tells you that the eigenvalues are independent of n. Then you need to show that the eigenvalues of A0 are proportional to t. Well, that's also simple too. You have that the determinant of A is this. Oh, have I got, yes, okay. So if I look at this fundamental relation and I add B naught, then the determinant of, then take away, well, I take the determinant of that problem, then I have this relation. And this relation is expressible in terms of the trace and the determinant. So most of this cancels out, and this determinant of A gives you more clues. And it turns out that the eigenvalues must satisfy this equation, so it must be proportional to T. So now we're in a very familiar situation. We have a fixed determinant. We have the semi-simplicity of the front matrix of A2 in terms of kappa 1 and kappa 2, and we have the eigenvalues of A naught are proportional to T. We're exactly in the framework. So we have essentially 12 variables. We've eliminated 5 by constraints and by transformations. We've got 2 taken out by the semi-simplicity of A2 and 2 in the semi-simplicity of A naught. And you've only got 3 variables. We can choose these 3 variables to be AN, BN, and the sum of. So this is a parameterization of the connection preserving deformation in terms of these 3 variables. But it doesn't tell you exactly, naturally what you can tell what the phi and psi should be. But it doesn't exactly tell you what the yn and the zn, which are the Panlevey transcendents, are. And in order to do that, you just need to transform it so that if you let yn, zn, and wn be these combinations, then you retain the exact parameterization of the linear problem that a person in the audience found, along with his supervisor. Okay, so this is the Jimbo-Sakai-Lax pair. It immediately follows that you could have found the B naught in terms of the connection preserving deformations, which is the just looking at the compatibility relation. But also what you have is that the Bn and An are expressible in terms of the Panlevey transcendent, which is also of interest if you're looking at orthogonal polynomials as they apply to random matrix theory, which is what Peter Forrester primarily looks at. Okay, so to determine this, you can either look at how the psi and the phi come out from the expansions, or you could apply your connection preserving deformations. And this is just one formulation of it, looking at the leading non-zero asymptotics of this this compatibility relation gives you what Bn naught should be. And B1n is proportional to minus T. That comes directly out of what the leading asymptotics of phi n and psi n are. So this gives you exactly your linear problem in T. Well, excluding this factor of minus T, which has crept in via our transformation, this is exactly the linear problem given in the previous reference, which was Jimbo and Sakai in 1996. Okay, so comparing entries. So you notice that, first of all, the kappa 1, kappa 2 are proportional to q to the n, or nq to the minus n. This is very important because when you go from n to n plus 1, it means that kappa 1 gets shifted by a q, and kappa 2 gets shifted by a 1 on q. But we also have recurrences such as these, which tells you if we translate what these omegas are and b's are and thetas are in terms of the y, we have a set of recurrence relations for the yn's. and the ZNs. Oh, I've gone a bit far. Okay. So, once you look at the compatibility relation, this is going to pop out. There are more details in the paper that we're preparing, and there are a few details in the original paper, of course. So back to the transformation, if you go from n to n minus 1, this is inducing a transformation of A7 and A8 go to QA7, and A8 goes to A8 on Q. If you look at the recurrence relations, that's the compatibility between the x and the n, you find that this is equivalent to letting yn minus 1 be delta n over gamma n. And that's in terms of the A matrix parameterization. And the Zn can be found using a similar formula. You can also consider the formula that goes from n to n plus 1, which is another canonical transformation in the orthogonal polynomial context. And that transforms it so that A7 becomes A7 on Q and A8 becomes QA8. And from the orthogonal polynomial context and from the recurrence relations, that's equivalent to this formula, which is a transformation. So this is a birational transformation of the y and the z. And here's the references. So Bjorn's recent paper, which is a bit different because it's orthogonality over a circle. I should also mention that there is a framework for Q differential equations by Ishmael and Chen. They don't get expansions. They use the recurrence relations to find out what the coefficients are in terms of the AN and the BN. Gasper and Rahman, of course, Jimbo and Sakai's QP6 paper. Magnus, which outlines how one finds the differential equation. Well, an adaptation of Magnus's work has been used in our work. And, of course, orthogonal polynomial references. So, that's all. It's a bit short.
In this orthogonal polynomial framework, you don't probably find full parameters.
No. As you notice, you've
Couldn't really follow what you did there, but
yes, you don't get.
There's a restriction on that.
There's a restriction. There's an implicit restriction in how exactly we've formed these θ1 and θ2s, and they are going to be linear combinations of the A's and the B's. But the fact is that we've found that they are proportional to T, and we don't know what they are.
Yeah, so it's not entirely correct, I think, to refer to these solutions corresponding to orthogonal polynomials as Penderweg transcendents. So Alexander Ritz always makes this point that they're rather Penderweg functions. Because, they're not.
It's not the full solution.
No,
Not at all.
Not at all. In fact, if you get a full solution, then you've made a mistake, I reckon.
that should be.
Yeah, that's right.
This way.
Exactly. These are not full solutions.
So you may have constructed some particular solutions.
Yeah.
Exactly.
And so what's the parameter n can take? What sort of values? N is
just integer. And
Non-
that's where the
negative,
integer
non-negative
shift comes.
integer.
It's the order of the
So this means that you start from 0 and half infinite.
Yes.
So what is the object y naught then?
What was that?
Y 0.
Y0.
Capital Y 0. That's the starting point.
Yes.
In your
It's got Y0 is automatically 1 over mu 0. And it's a
y
constant.
is capital Y, the solution of the linear problem.
Yes. Capital Y.
Yes.
In the, if I just go back.
but it's a
So
different
here,
image that refers to-
at 0, oh, I see. There's a problem here. This is not, so y1, you have to start at y1 because Pn minus 1 doesn't exist.
But you can put 0 there.
Yeah, you can put 0.
Yeah. I can.
But you used another 0 when you talked about y0, y infinity.
Epsilon.
Oh, yes, yes.
Epsilon n minus 1, 0.
Yes, y0 and y infinity.
What is y1, y0 then?
Oh, y0. What is y0? Yeah, because the expansions only give you what y infinity are, because they are expansions around infinity. But I'm not sure what y0 are.
I don't think that. So I had the feeling that you are dealing with some special solution of hypergeometric type.
Yes, yes. We are.
And well,
It's not the full solution, and I don't think you could get...
and also, but even in Jinbo Sakai's paper, they have constructed the
Hypergeometric
determinant of solution in terms 251.
Yes.
So what's the difference? I was puzzled because you were working on the Jackson integral
Yes.
interval from C for the interval of CA
Yes.
in your notation. So you understand? Because orthogonal polynomials for that case, a big Jacobi polynomials.
Yes.
I understand. That's right.
Yes. The
Not the little one.
No, but the polynomials themselves are big orthogonal big Q Jacobi orthogonal polynomials. But the integrals associated with, so the moments
Yes.
of the big Jacobi polynomials are 2phi ones.
Oh, really? Oh,
Yes.
I understand.
Yeah. It's just, I should say that it's not a full general solution and that they are still 2phi ones, as you expect.
I remember, Sakai-san, you had a paper also on
Determinant
determinant
from, yes,
of-
yes, yes. So that's a sort of interpretation of his determinant in terms of orthogonal polynomials, right? In my impression.
Yeah, it may well be actually. Yeah, that'd be interesting.
I'm not sure whether determinantal expression coming from this framework coincides with his.
Yeah, that's yet to be.
Maybe you should compare.
Yeah, that's something we should compare. Simon, yeah.
So in terms of the general scheme, the 8-parameter scheme, where are you in the coalescence or specialization picture? How many parameters are free here?
I'm not exactly sure because the theta, I don't have direct, I'm not sure how the theta are related to the other parameters. It may be that the theta may depend on the support, for example. I'm not sure whether I have 5 free parameters or up to 7. But it's definitely not 7. I don't think it's 7. That would mean that it would be a general solution, as Nomi would.
But you sit somehow on the walls of the wild chamber in this
Yeah,
picture,
I think
right?
Oh, yes.
Also, what is the name of the circle? I don't know.
A3.
Uh-huh.
So this is the associated surface of initial conditions
Yes,
is of
D5.
A3 type,
D5.
Yes.
and this is D5 symmetry.
Yeah, so
Sakai's scheme.
five free parameters.
But so you, as a canonical Q analog, you chose big Q Jacobi polynomial.
Yes.
But as you probably know well, that there is a very big hierarchy of Q orthogonal polynomials up to
Indeed.
8, 7, or 10, 9, if you go to the side of the bi-orthogonal rational functions.
Yeah.
And how, let's say, consider only the orthogonal polynomial case.
Mhm.
You can take Askew-Wilson function, Askew-Wilson polynomials,
Yeah.
for instance.
And
Then,
this is what Nick Witte is working on. So he's looking at the Askew-Wilson polynomials and considering the same type of deformation.
yeah. So in that case, what type of Q difference equation you should?
He's still working it out.
Uh,
So what type of Q difference equation
Yeah.
that you get? So here we've got, you're
What
saying,
type of Q-Pandova equations? Where, if you consider Askew-Wilson, the case of Askew-Wilson polynomials, in this case, Askew-Wilson polynomials are related to the linear problem, right?
yes.
So in that case, where where do you come to? Where in the Sakai scheme, for instance,
Yeah,
will you come to?
we're not sure yet, is the short answer. We suspect, so you know the Yaski-Wilson polynomials are McDonald polynomials. We're not sure whether we should get the full E8 or A0 if you wanted to refer to the surface, or we get something like E7. We aren't sure yet.
So is it already clear whether the moduli space is two-dimensional, essentially? I mean,
Yes. I can't answer that, sorry. I don't know. Nick's has been very secretive about his work, and I can't answer that for sure.
Can you show the weight function again?
Yes. The weight function is there.
Where's the t sitting?
The t is
Oh, wait a
sitting
minute, I
here.
see down there. Yeah, okay.
So as I say, if you take, so here it tells you that t is proportional to 1 root and 1 pole of the determinant.
This is also reminiscent of how you get the Toda equation from having
Yes.
t dependence in your recurrence coefficients.
Indeed.
For instance, in Ismail's book.
In Ismail's book and in Chen's work, they often get Toda type equations.
It's similar idea where you put a factor exponential minus xt in the weight function.
Yeah, that's in the differential case.
Yeah. So
Indeed.
this is somehow a generalization. Can you do with it?
I haven't seen Q-Toda equations, for example, but we haven't looked in that direction. We've mainly been, yeah, I suspect it might be, you might get Q-Toda equations, for example. But that's yet to be seen. That's something for the future. Are there any more questions?
You are your own chairman.
I know. Since Rod's away and Reinhardt's away.
Then let's take the speaker again.